The title of the talk that I came up with is Some Musings on Teaching Reproducibility. Now, as a strong warning, I have opinions, and I'm going to be sharing them with you. That does not mean that they are proven facts. It does not mean you have to think that they are absolutely true, but I have strong opinions about the way that things should be done, in my opinion, and I'm going to talk about some of that, and you are more than welcome to push back on some of it. I am a self-admitted nerd. I am a techie, I am a geek. I have been programming for the better part of 25 years. And to me, this is a sort of a natural way of thinking. And I realize that's not the case for a lot of my professional colleagues. And sometimes there's a bit of an uphill battle in sort of showing you why certain things, I think, should be the way that they are. So some connections here. These are how you get in touch with me if you want to. This is the website. And these slides are, as someone noted, Zeringen slides built off our Markdown. And they are on GitHub, which I put into the chat just before I was promoted. And I hope you can all still see that link, and you're welcome to go there and follow along. And if you actually go right to my GitHub, you can actually see the source for these slides as well. So quick background to kind of put us all on the same page, because we haven't really talked about this much since this morning. And even then, my viewpoint on this is a little bit different to Chris's this morning. So in this talk, I'm specifically interested in discussing the ways that we can encourage students to build skills and habits for reproducible research methods, specifically with respect to the way they gather the data, the way they manipulate the data, and the way they perform statistical analyses of the data. I'm going to leave the whole discussion of general reproducibility in the psychological sciences and the issues your field faces to the domain experts who have to figure this out. I'm not going to try and parachute in and tell you how to live your lives. So what I'm specifically thinking about, and I'm narrowing the scope here, is a specific framework that started and was first published by Claire Bout and a research team at Stanford as part of geophysics. And it was this document that was in the proceedings of the 62nd AGU, which was held in New Orleans, and its electronic documents give reproducible research a new meaning. You got to remember the context here, right? Computers and their evolution. By the time you get to 1990, pretty much all researchers in the geosciences, at least, had personal computers in their offices, as well as mainframes down the hall. And so it was becoming ubiquitous. And some quotes from this paper. A revolution in education and technology transfer follows from the marriage of word processing and software. Researchers can reproduce their own results a year or more later by pressing a button. And our basic goal is reproducible research, and the electronic document is our means to this end. This is the DOI for it. It is one page. It is absolutely worth knowing that this exists, just to know your history, because we forget that this wasn't possible until a certain point in time, and then it has now been possible for 30 years, and maybe it's time we all kind of adapt. So the definition that I want to go with is that sort of the one on Wikipedia. Scientific results should be documented in such a way that their deduction is transparent, with a detailed description of the methods, and this is the key, and this is where we as scientists and as a profession fail, the full data set and the code used to calculate the results need to be easily accessible. This is open science. And I was tempted to put some things from some of Carl Broman's talks. Bethany will know who that is. Most of the rest of you probably won't. He's a statistician at the University of Wisconsin, and he has some very strong opinions about reproducibility, and he's done some great talks on it. But you know, the idea that data is available upon request needs to die a death. It needs to be gone. We need to stop that. It has to be released if it's not controlled, if it's not something like health data that's somehow preserved. But even then, the scripts that are used to produce the results need to be shared. Otherwise, no one can trust your results. And we get to all the problems that Chris mentioned this morning and all the things that we're all aware of. So what's required to do this? To make a project computationally reproducible, the data in the files have to be separated from one another. They have to be labeled with metadata. They have to be documented as to where they came from, what their provenance was, and so on. All operations in the process of converting the data into actionable results should be automated as much as humanly possible, with manual intervention killed. The workflow should be designed as a series of logical steps, so that when you run one step, the output of that step feeds into the input of the next, and so on, so that there's a flow through the analysis, as we all know there should be in a properly done analysis. And you need versioning control. You have to be able to track when the changes were made and how they were made and who made them. You You can't just trust that, people's naming file convention will make any sense. And this should include data acquisition, data processing, including the manipulation and filtering of the data for removal of outliers and miscoded, misrecorded, and so on data. And the analysis itself, and this is obviously where I live, is this section, but the computation of your statistics, the creation of your figures, the model fitting, including the interim steps and the decisions you made. Avoid the garden of forking paths. Don't let yourself do things not recorded and pretend that you never did it. A linear flow, avoid modifying earlier steps, and avoid arcing. Make your statement, run your analysis, make your conclusion. So from a researcher point of view, if you hear all this and you're like, yeah, that really, that sounds like something I should know more about, I strongly endorse data carpentry, and the link, this is a link, no, sorry, link is there, which are workshops that can be run regularly and will teach you the basic skills in doing this with best practices using modern tools. So even if you don't do this for your research personally, maybe your research doesn't involve a lot of data, if you do statistics, you really should, but that's not the right thing. If you want to teach it properly, you got to know something about it. You can't just wing it. And so I strongly endorse the idea of physician heal thyself. We should be better, and then we should teach our students to be better. So this sounds daunting, I'm sure. Like I said, I'm a nerd, and this is very much my wheelhouse. And some of you are psychologists, and you're never taken a computer science class, and you're not a coder, and this sounds daunting. But there are ways you can take baby steps to bring yourself toward this, and then you can share those steps with your students, and we can make this a slow process. Force yourself to organize your course materials in a coherent manner when you're preparing and organizing a course. Maybe learn to use Git to store your course materials, and then that means you can share your course materials with other people. And that was a discussion we were having in the last hour, like, what can we all do to make our materials easier to produce and avoid duplicating effort, and really encourage each other to do better work and better teaching. We can create your slides for your course in something like our Markdown. It's a little step, and the students won't know the difference, but for your point of view, it'll help you learn, and it'll give you that reinforcement that you're constantly using a product like this. You can integrate software into your lectures themselves and in the classroom, not in labs or workshops or under the supervision of a TA with that disconnect between the theory and the practice. Bring it into the classroom, experiential learning, get the students doing things in real time with you, or at least demonstrate that to them as part of your teaching. And just always be learning. Accept the fact that the world is changing way faster than any of us want it to. And we have to constantly be worrying about things changing and updating our skills. I'm just going to take a moment and check. There are no open questions. Good. Okay. So some inspiration for you, some quotes from some sort of world leaders in this area. Jenny Bryan was a professor at UBC in statistics, and she now works for our studio. And she, in one of her talks, she leads off with this inspirational quote. She says, look, file organization and file naming are powerful weapons against chaos. They help you control the flow of the scientific method. Mark Holder was quoted to say, your closest collaborator is actually you from 6 months ago, but you from 6 months ago, you don't reply to emails. You're a horrible collaborator. So when you're organizing your things, you got to think about the fact that you're going to need this later. And when you come back to it, you want to be able to understand what you were doing, because in 6 months, it's all gone from your mind. So some basic principles to think about, and this applies to the creation of teaching documents, the creation of research, or even small projects for your students. Slow down. Document your steps. Have sympathy and thought for the fact that someone's going to need to look at this in the future, and it might be you. And have a system, whatever that system may be, and follow it. So how do we translate this into teaching, and how do we bring this into our classroom, and how do we teach our undergraduates to be inspired by this and to think about this and to realize this is a paradigm for organized, reproducible, replicable science? Well, let me start with what not to do. And this is where my opinionation is coming in, okay? So take this with a grain of salt. Stop using mathiness. I see people teaching courses where they include formulas, incredibly complex formulas with no context, no derivation, and the inability for students to actually understand what's going on because their students don't have the math background to actually be able to manipulate the formulas properly. If your students haven't taken calculus, you can't include something that relies on maximum likelihood because they don't understand what's happening. If your students don't have linear algebra, You really shouldn't be including any formulas that have to do with a linear model, because it's all solved using matrix equations. So just get rid of the mathiness. We don't need it. You know, the students will never use it again. The actual supposed intuition that is gained by manipulating these formulas is massively overrated. And in the end, it's often taught poorly because instructors don't understand it themselves. So eliminate as much of that as you can. Stop using lookup tables. It's not 1965. There's a lookup table in the back of your book. Stop using it. Have the students compute the quantiles that they need for things like Z-scores using a computer, because it gets them into whatever software environment you're using and it gets them comfortable with the interface. And yes, it's one extra step, but then you're not avoiding that whole class where you try and teach them the inverse lookup table method. When are they ever going to use that again? Just get rid of it. Scrap it completely. Don't teach Excel. And I realize we've had a lot of discussion in the last 2 days about Excel, but Excel is not a tool for science. It is a tool for business. It is a tool for accounting. It is not designed for science. It does not do statistics well, and it has a very hard cap at the top of it as to what it can and cannot do. If you get to the level where you're implementing statistical algorithms in Excel because it doesn't have the built-in support, at that point you have the skills to do it in anything. Why would you do it in Excel? So stop teaching students such a horrible tool to do analyses. Now, Excel has a place, data gathering. Spreadsheets are great for data gathering, but they're not to be used for analysis. And that's my strong opinion, and I'm taking a strong stance on it, and I realize your reality is different to mine. But I forbid it from my classroom for these reasons. Don't teach menu-driven systems. I realize that they're strong, and I realize most of psychology still uses them, but menu-driven systems that don't have recorded, documented steps attached to them are not reproducible. You're teaching your students bad habits. You're preparing them to only be able to do what someone else has prepared for them, and you can't reproduce a menu click. So unless it's something like JASP, which very sensibly has an analysis pipeline built into it that records what you've done, you got to stop using them. You got to get away from them. If you're going to do them, the emphasis has to be on understanding the entire process from start to finish, from data load to plot creation, and that needs to be the emphasis, not the actual act of creating it. And in that case, then it's fine. But if you do this, it's just teaching people to poke around in a system until they get a result that they like. It's bad habits, and we need to stop. Don't use horrible code. If you are going to use something like our code, don't use code from your PhD, which was N years ago. You have to update your examples. You have to update your data. You have to update the way you approach your problems, or it will look horribly out of date to the students, and they'll say, well, what's the relevance here? This is clearly out of date. And unfortunately, when it comes to coded stuff, things have changed a lot in the last decade, and you have to update your examples. Don't use examples that are so small that you can type them out manually. You need to, by osmosis, get your students thinking about the fact that most data sets are too big to do that. Either there's too many variables or there's too many observations or both. So use file input output, read in those CSVs that you gathered from somewhere. Give them data that's a little bit too big to really get your head around all at once, and teach them to work with the reality of real data. Don't use fully clean data. It's misleading. It hides the nitty-gritty. It hides the fact that measurement observations happen with errors. Outliers are a thing. Force students to confront the reality that data is not magically clean when it is given to them. And here I have something to lighten the mood a little. On the left, we have the data with no prerequisites that are typical for statistics textbooks. And on the right, we have data as it actually exists. And students need to know that there's actually a grizzly bear out there ready to eat them, not a tiny teddy bear. Now, the standard structure of tidy data, and this is a concept, tidy data was popularized by Hadley Wickham in a paper about 6 years ago, is that tidy data sets should all kind of be the same. Columns should be laid out as variables, rows should be laid out as observations. Messy data sets could be anything. And one thing we can do by modeling this and bringing these data sets into the classroom for the students is demonstrate that you can encourage your data to kind of be manipulatable by encouraging tidy recording. And then everything's organized and it's that much easier to keep track of it. Again, it's about the system. And so you kind of just say, well, look, this is how data should be laid out, because it means that we know what the pieces are without having to think. And then when you send them out, if you do, to record their own data, you say, look, it needs to be tidy when you record it. Don't make the mistake. So this leads me to the point of the talk and what you can do to kind of try and encapsulate a portion of these ideas all in one spot, and some experiences I've had doing it are marked down. So when you're using lab work and you're actually in a lab, whether that's a bio lab or a life sciences lab or a psychology lab or a sociology lab, whatever you're doing, when you're doing actual research at the graduate or the PI independent level, we use notebooks. And what do we use them for? We organize our methods, we organize our results, we record our results in those notebooks, we jot down conclusions, and traditionally speaking, at least in the engineering world where I came from, you sign and date every page because that notebook may be evidence for a patent application. And so you keep track of it and you're not allowed to rip pages out. You're not allowed to, insert something later. It's all got to be recorded properly. You need provenance. We then take these notebooks and we put them in the methods sections. We write down what we did and we cleaned up a little bit and we turn it into the scientific language, but it's there. So when you're working computationally, why would we do anything different? Do the same thing. That method was developed over several hundred years as a logically internally consistent method for recording our scientific process. So data provenance, where did it come from? Who touched it? What sort of manipulations and conversions have gone on with it? What workflow happened? What steps did you take along the way? What were the tools you used at each step? How did you use them? What were the parameters? What were the arguments? Keep those researcher degrees of freedom under control. Record all these pieces that you're doing. And what software did you use? And not just what did you use, but what version was it? Because sometimes things change between the versions. And if you want to be able to reproduce it later, you've got to know these things. This can all be sort of encapsulated in things called Docker. And there's all these advanced things that people are developing now, our environments and so on, where you can do all this all at once. But you don't need all the fancy tools. You just need the logic of, okay, if I wanted to reproduce this experiment from scratch, I need to be able to start with the raw data, and all of the analysis steps should flow. So what does this mean? Well, in my opinion, again, opinionated, right? This is my opinionated opinion. Students need to access these within the first course where they're exposed to statistics. You cannot leave it for a later methods course or an advanced course. It has to permeate every aspect of the way we teach these undergrads. You can't hide it away. You can't trust that they'll somehow magically pick it up later. It has to be put in there deliberately, and that's our job. We are their teachers. We have to teach. You have to immerse them in it. You have to give them support. You have to tell them, yes, I know this is a lot, but what we're doing is we're taking the world of science and we're bringing it into the world of computation and statistics, and we're using all the same principles you know from having taken labs in all of your high school and early undergraduate courses. We're just doing that when it comes to stats. So traditionally, if you wanted to include R in your intro course, and this is why those slides from earlier today showing the growth of R, this is why it took so long. This meant you needed to use the baseline R GUI, which is a horrible example of user experience, or R Commander, which is not terribly much better. You have to teach students the code. There was no support, no scaffold. You jumped in the deep end and there were sharks. And I totally understand why people then were like, no, I can't do it. I cannot expose my students to this level of pain. But this has been fixed. And it's time to acknowledge that fact. We have created notebooks, and they are the equivalent of a lab notebook, but for computational analyses and statistics. They freely mix text, code, which replaces our math formulas in our notebooks, figures, which replace the diagram, analysis steps and decisions and logical findings and inferences, and our results. And additionally, when you stop using it as an interactive notebook and you treat it instead as a document, they are set up to force computational reproducibility. Because when you click that button in our studio that says knit, or the equivalent in any of the other platforms, it clears your environment, wipes out your temporary steps, and iterates your document linearly from the top. And if you did anything that didn't get recorded, it will then break and make you aware of that fact. Here's an example. This is my talk from today. This is our markdown document in our studio using Xaringan, which is an R package and the Xaringan themer. And this code made these slides that I'm using right now. Every single lecture that I present via slides is done this way now. And they're all put up on GitHub for free. And my students can download them. Every workshop I run in my class, done this way. And I immerse them in this environment. And I've had some pretty good results. So some advantages. The code's right there. You can see exactly what was done. You can see the arguments that were made. You can see what was done and how it was done and in what order. You can insert your figures right there in the middle. You can have some discussion of what's happening, and then you can have a line where you generate a figure and then you talk about what the figure means. You can run your models, get your results, look at your residuals, do all of the stuff that we do when we're model building right there. Syntax is there, and anyone who knows that syntax can look at your work and say, oh, okay, I see what you did. Oh, why did you do that? Oh, okay, and then they follow along, and it's all there, and all of your decisions are laid out. It's not just a figure with no context. And as Bethany was mentioning, and this is sort of true of anybody who's ever entered the world of experimental X and has tried to reproduce someone else's results, papers are kind of shit. And most of the time you read a paper and you're like, so how did you do that utterly critical step 3? And there's no details whatsoever provided. This is better because you can see every single step, every single logical thing. It's a good framework for working in. So what are the advantages of it from the student point of view? Well, it forces them to think about their workflow and the steps that they're taking. They can't just flail and hope that something comes out the other side. It integrates all your decisions and all your things in one spot. It teaches you coding skills by stealth. And this is sort of an important idea from statistics education and sort of the education literature as a whole. The idea of teaching by stealth is that you don't make it an obvious outcome of teaching. You don't make it an objective. You just immerse the students in it and show them little bits and pieces. And before they know it, they're learning without even realizing they're being forced to learn. You template it, you scaffold the work, and then you expose it at the end, like pulling back the curtain on the Wizard of Oz. This is actually how most researchers do their work, is they build these sort of workflows, even if they don't do it formally in a document. So you're giving them best practices right from the start. And this is the really important one, there's no limit to this. You can keep pushing this as far as the scientific world allows you to do so. There's no limit like built into, say, SPSS, where it's like, well, have they implemented that particular variation of the algorithm I want to run? If they haven't, well, you can implement it yourself, but now you're going down a rabbit hole. Whereas in R, you're like, well, is it on CRAN? And we're at 18,000 packages and counting, which do anything you can imagine. And that's my last point, is CRAN. CRAN is an incredible resource, and don't overlook the importance of it. So just checking. Someone has listed a lovely collection of interactive visualizations. And yeah, take a look at those and see if they're useful to you. Share and share alike. Like I beg, borrow, steal, and rip off material for my courses every day. And if somebody else has done it, great. I am going to steal it from you happily, and I hope you will do the same for me. So let's talk about my course, or my courses, and how I've done this, and sort of what happened. So Math 1051 and 1052 at Trent are large introductory first-year statistics courses for general science majors. They are mostly mandatory for people who are not in stats, not in math. They're taking it because they were told to take it. It's part of their curriculum. And what my job is to prepare them to be able to do their field of science. So on the whole, these are big classes by Trent standards, so 650 students and 450 students in a given fall-winter sort of setup. Obviously, that's nothing to U of T or to York, but you can imagine this as being a good solid, large section of a course, and scale up from there. Students the vast majority, have no calculus. They've never taken calculus in their lives. They definitely have never taken computer science. They think computers are scary, math is scary, and they're terrified to be here. And they're taking it because someone told them they had to, or they cannot get their biology degree, environmental science degree, forensic science degree, etc. So what did I do? Well, over a few years, this is how we've evolved the course. We have regular lectures. It's different with COVID, but regular lectures. And we have weekly workshops. They're 1 hour long, and they come to workshop in small group sections led by a TA with pre-written, provided our markdown documents, just like I sort of waved at a minute ago. And it's text and code and results all mixed together, and the TAs step them through the logic of how it was created. They run the chunks of code themselves. They see how the results are there. They stop, they manipulate, they change a few things. They see how it affects the plot. and they learn. Slowly and scaffolded, they learn. And then in those workshops, there are challenge problems that they can try, and there are additional Learn R tutorials, and they can be downloaded, and they're an interactive question and answer system built into R that students can run on their own. They're not for points, they're just there for them to practice. It'll ask them a question and ask them to provide the code that would do that, and it's all taken directly from the workshop of the day. We then step that up, and there are weekly self-graded Webwork-based assignments. And Webwork is an open source system from the Mathematics Association of America, which allows for asking computational questions that are dynamically generated for every student. The students get their own unique questions with unique numbers, and it mixes some multiple choice, some theory questions, and questions which absolutely force them back into the R environment and force them to use R in the way that they've just been demonstrated. And so in week 3, say, of 1051, we introduce the idea of quantiles for distributions, and we talk about how we need to compute these things, and we form these probability statements, and then we say, yeah, so this is an integral, and we know you don't know how to do an integral, and that's okay. We're going to tell the computer to do the integral for us. Here's the syntax, here's the code. And then on the next couple of assignments, we have them computing quantiles, and they go off and they do things like compute integrals or compute derivatives and inverse integrals, and they find quantiles and they find probabilities and they work with it. And by the end of those couple of weeks, they're ready to compute z-scores and all the rest of it later on in the course. Then there are 4 large written R Markdown assignments turned in basically every 2.5 weeks, and they are given a blank sheet. They're like, create an R Markdown document. No, we're not going to do it for you. And then answer the following questions. And all of the questions are based on the workshops. And if they've been coming to class, they're pretty straightforward. And most students end up being like, oh, okay. And they figure out how it's supposed to work. But they create it themselves from scratch every time. And by the second one, every question requires the loading of data from a file provided. And we mix and match CSVs and text and Excel all through the semester. And by the end of the semester, they can load data from all of these sort of formats. And then there's R chunks included in the lectures. So in my lecture slides, as I'm going through the class, all of these R chunks all the time being discussed. And it's just osmosis, osmosis, osmosis. We just expose them over and over and over again. Now, downsides. Tech support is complete chaos. Bethany mentioned this too. There was a product called RStudio Cloud, which is an amazing product and got rid of almost all the tech support and just got them right into R on the first day. Unfortunately, they just moved it to a paid product this past summer, about a year ago now, and they have not aimed the price point at anywhere in Canada that can afford it. The Ivies are probably fine, but we can't afford it, so I can't use it. The learning curve is very steep. Students need to be supported in this, and they need to be warned, and they need to be given lots and lots of encouragement, because those first few weeks scare the crap out of them. Grading has to be generous to start. Your first couple of assignments need to be quite gentle, because otherwise, if you harm them too much, they're just gonna drop the class. You got to get them in and kind of lull them into a sense of, okay, I'm learning this, I'm gonna be okay, before you start ramping up the difficulty. And you absolutely 100% need qualified, tuned-in TAs. You can't just use whatever arbitrary graduate students were assigned you from your department. You can't just pick a rando off the street, you know what I mean, to be your TA. It has to be someone who can walk the talk, walk the walk, and talk the talk. It has to be someone who knows how to use R Markdown, who knows how to use RStudio, who's comfortable with the kinds of common errors that students will run into, who could do the assignment on their own with absolutely no support in about 15 minutes to be there supporting the students and stepping them through. So I train my own TAs. I can't trust my university to provide me graduate TAs who have the required background, and so I train them myself. And ideally what you do is you have your own graduate students, or you'd have quantitative oriented graduate students from your larger programs. Results though, 85% of the students fully engage, learn, do great. My failure rate's fairly low, and by the end of the semester, they're excited. They're really pumped about what they've been learning and how they've been learning it and what's possible. And you know, obviously a bit of that is us like really rah-rah-rahing things, but they engage, they learn. And these are not mathy students. You know, they may be very slightly more technical than your average psychology incoming first year class, but not a hell of a lot. These are bio majors, these are environmental science majors. They've never taken calculus, they've never taken computer science. They think they're gonna hate math. And then they show up at this class, and the results at the end of the semester are like, they're like, wow, I feel like I learned a ton. I feel like I'm ready to use this in my coming classes. And anecdotal evidence from my colleagues in these departments is that these students are successively becoming stronger and stronger every year as we refine this course, and are able to do more and more in their experimental methods classes. Students are able, by the end of the first semester, to create professional or markdown knitted documents entirely from scratch with full worked analyses of scientific data using a variety of statistical methods. They can load data files, they can look for abnormalities, they can plot exploratory analyses, they can compute simple statistical models, including linear models and basic tests. They can do NHST across a variety of examples, generate confidence intervals, and produce quality plots across a variety of different plot types. That's after 12 weeks. By the end of the second semester, they can do all of that above, plus they can load even more data set formats and more varieties of formats. They can do linear and multiple linear regression, as well as generalized linear logistic models. They can do one-way and two-way additive ANOVA models, full from scratch, from raw data right through to the end, looking for the assumptions, checking things. They can do interactions, interaction plots, discuss what the implications of these things are, look for them in F tables. They can do post hoc tests, and they can do an even broader selection of the standard families of hypothesis tests. And then, as well, they can do permutation nonparametric testing as well, including writing their own for loops and computing these things from scratch, as well as even more plotting. So 24 weeks, and I can take complete novices and turn them into this. And then they go on to their upper years, and I'm getting, as I said, anecdotal reports back from these students, from their instructors, that they are able to blast through what was formerly considered hard methods courses, because I've done so much of it already with them, and they can just do it all in our Markdown, and it takes no time at all. And I get these reports like, oh, it took my friend 4 hours to do this lab because they wanted us to use Excel, and I asked, and they let me use our Markdown, and it took me 12 minutes. Things like that. And it makes the students excited. They feel like they've been inducted into some sort of secret society that understands the value of using a computer and what it's really for. So here's some extra examples. These are just from the last assignment of the semester, from this last semester that I just taught. Student loading data off an XLSX spreadsheet, looking at it, formulating a hypothesis test, just a simple one, talking about what it sort of means, and then recognizing the kind of test that they should do and computing it from scratch using the algorithm without using the built-in t-test. Another student, on their own, went off and realized that Markdown supports the creation of really slick-looking tables, moved the data from the assignment into the assignment questions into the R Markdown via these nice-looking tables, so it looks really pretty, and then ran a chi-squared test comparing the distribution of the digits, and then discussed what that means. Another student, loading data and then creating an interaction plot for a two-way ANOVA, looking at pulse rates across ages and genders, and discussing what that means. Now, I'm a statistician. I work with and write statistical software every day of my professional life. I have 9 or 10 packages to my name. Like, I know what I'm doing with all of this. But software is eating the world. And there is a link there if you want to follow it to sort of read up more on that. We owe it to our students to prepare them to use the actual tools of science, not as used today, but as will be used in their careers. So even if it's uncomfortable for us, we have to adapt, we have to change, we have to grow. Our current best practices, or whatever cuts it now, will not be the same in 5, 10, 20 years. Realistically, let's all be honest, they're probably not okay now. You know, we get busy, we get behind. This approach does work for complete math-phobic novices. You can do this. And it is actually genuinely amazing to see how comfortable some of them have become by the end of the year. So how do we go about taking professional novices, us, and turning us into people who can do this sort of stuff confidently enough to be able to integrate it into our teaching? Start by just trying to use a little bit of our Markdown, a little bit of our studio in your class. Get your feet wet. Do it in a way that's, you know, the last 3 or 4 years. Don't use examples, like I said, from your PhD too long ago. You got to integrate it. You got to make it seamless. It can't just be a bolt-on. You can't put it in a lab and fire and forget and just hope the TAs can handle it for you. It's got to be in every lecture. You always got to be hammering it home. It's got to be osmosis, osmosis, osmosis. Take those little students and put them in the brew of R, or whatever language you choose, whatever program you choose, and just immerse them in it. Everything you do needs to be about this like drumbeat of reproducible work, which is written in a way that someone else can understand what you did. And this is, again, why I hammer home Excel is not acceptable. Because when you do work in Excel, cells get slid around and there is absolutely no way to track that. You do something to manipulate one data point, there is no version control to tell you that you did that. We've got to enforce this idea that data is synchronized. Once the data is recorded, you never touch that file again. If there are outliers, that's fine. You deal with them in the first step of the analysis pipeline. You don't change the raw data. Then the provenance is gone. Leverage the big data movement. Bring in big data, data that they would never be able to type or gather on their own. Big, huge, modern, messy data sets. Inspire them, excite them, show them what's possible. Even if you say, look, we're not going to get to this in this class. Obviously, this is way beyond the scope, but look what we're aiming for. Look where we're going. This is what we want you to prepare the skills to do. And just always be learning, accept that you need to. If you want to use this kind of stuff, if you want to teach statistics, you have to accept that statistics is a young discipline. It's younger than psychology, formally speaking, and it is evolving very quickly. And teaching the methods that you were taught in your PhD will not cut it. We're changing too fast, and you're dated. So some good references. There's material posted. There's an incredible amount on the internet. These are just some selected ones. There's an R Markdown 3-hour training session thing that you can run through. There's the Data Carpentry Initiative. Really strongly recommend that once COVID's over. If you have the chance to go to one of those, they're amazing. There's a Coursera course on reproducible research and using R Markdown for that. And there's a book, The Definitive Guide to Using R Markdown. In addition, sorry, I don't know where I put it. I have it here in my office. I was just looking at it the other day. There's a book on reproducible research with R. It actually goes through a lot of these philosophies. It's a $45 book. It's worth buying. And then some references that I looked at when I was reminding myself of some of this, the curriculum from the reproducible science movement, the paper by Goodman, Finelli, and Ioannidis. There's an IEEE edition from engineering, which some of you may not have seen, on reproducible research in the engineering sciences, which has some really interesting discussion. Shout out to Dr. Allison Horst, who did that awesome animation or picture that I used there. She has these amazing illustrations. They're all completely free and you can embed them in your classes. Some of them are extremely cute and it's totally worth doing. It brings a little bit of levity to your class. Dr. Albert Kim has a beautiful talk on the idea of tame data, which is this idea that we have wild data, that's the grizzly bear, and then we have tamed data. It's not gentle, but it's most of the way there, so it's small enough your students can actually get their hands dirty. And then anything Mina has written. So Dr. Mina Setinkaya-Rundle is a professor at the University of Edinburgh, and she has this incredible breadth of stuff that she's done on data science and statistics and modern methods, and she's an amazing person, and basically anything she creates, she has a massive GitHub. Go check it out. She does much cooler stuff than I would ever dream of being able to do. So feel free to contact me if you want to talk about any of this. The slides were created by Zaringen, which is a really cool package, and these are available on GitHub. And I'm going